forget. I forgot to record one of my sessions yesterday. At least it was the second video, but I still forgot to record it, so now I have to re-record it. Yeah. Okay. So right before we left off on Monday, we're talking about the photoelectric effect. So once again, when I was learning this as a student, my biggest goal right then, I was a pre-med, so my biggest goal was learning the information, making sure I know it very well, and that way I can reproduce this information if it comes up on the MCAT, because I realized back then that they don't just ask conceptual or theoretical stuff, they ask lab stuff too. So you want to know, you don't just want to know the information, you want to know how it applies. So they have problem solving questions. So my goal was just memorizing, to remember, to be able to solve problems, to get a good score, all that stuff. That was my goal as a student. And then now I'm not a pre-med anymore. My thing is, how can I monetize this, right? Now I realize all of a sudden you got to get a job, you got to get paid. My attitude is different. Well, before I started thinking about monetizing it, business majors, the people who knew people in business majors, took the photoelectric effect and monetize this. So how do we see the photoelectric effect in our lives every day? If you have anything solar in your life, solar uses this technology to produce electricity from ultraviolet rays or sunlight, right? Yeah, every time I think about how chemistry or different areas of science is being applied to our lives every day, and how somebody is banking from that, and I'm like, I don't know why I didn't think that way. We just weren't taught to think that way when we were in school. It was always learn the material, and you make it in life. You know, I mean, I've made it, but I wanted to make it differently. You know what I'm talking about? Okay, so in the photoelectric effect, what we learned from there that we apply to the quantum mechanical model, Einstein proposed that light energy was delivered to the atoms in packets called quanta or photons. So even though we're looking at the behavior of light like a wave, light also has certain particle nature, which is light is delivered to atoms, even though it's a wave, in packets, in quantized form. So the term quanta here just means specific amount. Okay, quantized, quanta, quantum, they're all kind of around the term specific, right? So when light is being delivered to atoms in specific amounts, what they're saying is you don't have a continuous flow of light energy being exposed to the atom. You actually have, the best way I can think about it or describe it, it's bursts. It's like on, off, on, off, on, off. It's some kind of sequence, right? But it's not a continuous flow. So there is quantized amounts of light being delivered to the atom. So the quantized amount of light, or the pockets or packets of light, is called photons. And essentially, bottom line is the atom will accept this light waves in quantized amount, and then stuff will happen, right? So as we're looking at this right here, we're looking at the relationship between the energy of the light, and then H is called, so E is energy. I'm going ahead and defining this. Let me raise my table a little bit. H is Planck's constant. So remember, Planck was the scientist who did the experiment we just talked about, the photoelectric effect. He worked with Einstein too. And then we have the V here. This V stands for the frequency of light. So there is a correlation, or there is a relationship between the frequency of light and the energy of light. We see the relationship again, and of course they're directly proportional right here. Okay, so we're being told that the energy of light is proportional to the frequency. What does that have to do with this right here? The amount of light, the energy of light absorbed by the electron determined the speed with which the electron will escape from the metal surface. If the electron got a lot of energy, the electron escaped the surface really fast. So when I was learning chemistry, I started realizing I could bring in my quote-unquote non-chemistry life to help me learn the chemistry, because I like to relate to what I'm learning, right? When I started to realize this was working, because my teacher showed me how to do that, I started bringing my non-chemistry life to chemistry. I used to be a runner. One of the things you did as a runner was, well, you run off blocks if you're sprinting, right? You kind of sprint off blocks. So I kind of think of the electron as doing that when they're starting the race, or well, the electron is sitting there, right? It gets some energy from the light. It absorbs the energy. Depending on how much energy it gets from the light, it uses that energy to sprint off the surface of the metal. And the more energy the electron gets, the more it sprints off. So it's not just coming off slowly, it's being ejected forcefully depending on the amount of light. The frequency of the light can make a difference too. So we're being told here that the frequency of the light can influence the energy. Okay, so remember, the frequency sometimes relates to the color of the light or the energy of the light. So it's not just light, but also the type of light based on the frequency. Okay, so we're being told here the energy of a photon, which is the energy of a light. That's another way of saying the energy of light. Remember, photon is the fundamental particle in light, is directly proportional to its frequency. So we are picking up where we left off from here, right? Energy of light is proportional to frequency. So if you get light that has high frequency, you also have light that has high energy. So frequency and energy are directly proportional. We also learned this before, that frequency was equal to speed of light over lambda. So if energy is proportional to frequency, energy is proportional to speed of light over lambda. Then in chemistry and in math, if you want to change the proportionality sign and get an equal sign, just replace this with equal, and either a constant. In this context here, our constant is Planck's constant, so I'm going to replace this left side here with equal and then h. H is the Planck's constant. Anyway, from this relationship here, we get this equation. Okay, so we started with energy is equal to Planck's constant times frequency. And then we replace this frequency with the equation we had earlier, and then we get this. So we have two different equations that we use as we need. Okay, so the other thing in chemistry, remember, the equations are used per the context. What are they asking you in the question? Are they asking you for energy? Okay, if they're asking you for energy right now, based on what we've covered and based on the slide we're looking at, there are two possible equations you can use, the one to the left or the one to the right. How do you know which one to use? What other information have they given you? If they're asking you for energy, solve for energy, right? But they've given you frequency, then you want to use the equation on the left, because Planck constant, or Planck's constant, is a constant that's known and it has a specific value. So I'll actually suggest that you write this value down. This is the value of Planck's constant all the time. Okay, so in the question, if they don't give you Planck's constant because they assume that you have access to Planck's constant and you know what it is, notice the unit of Planck's constant is joules times second. Okay, with me not having the greatest memory and realizing at some point in my life, oh, this is the reality of my life, right? This is, I guess you can call it my truth. I wasn't speaking like that when I was younger. This is the reality of my life. My memory isn't the greatest. I have to use other means to remember. Not the way my friends were doing things. They would just read stuff and remember it tomorrow, not me. Mm-mm. So I have to relate things, right, to what I knew. In education, they call that building schema. If I relate what I know to what I'm trying to learn to what I already know, it made it easier for me to recall it. Okay. So when we're looking here, by this time I had figured out dimensional analysis, and it was important for me to know the units of what I was working with. Energy is usually measured in joules. So think about it. E is joules. We just learned the value of Planck's constant. H is 6.626 times 10 power. Was it negative 34? Yeah. Negative 34 joules times second. Okay. Since E is joules and H has that unit joules, times second. For me to get joules on the left side by itself, I have to multiply this by some unit that is 1/2, right, to get rid of the second. So I went from hating dimension analysis to loving it because I realized that dimension analysis was the key to my memory issues, which is not remembering stuff a lot just by regular memory routes. Dimension analysis helped me to logically figure out if I've forgotten a formula or I'm kind of messing it up. It helps me to make sure I have the right formula, right? In dimension analysis, it says if energy is in joules and you're multiplying two other measurements to get joules, then the units have to cancel out and leave you with just joules, right? 1/s is frequency as far as the units is concerned. So that confirms that this formula works. If they give you frequency in the question and they don't give you Planck's constant, you can use the Planck's constant to get joules, okay? If they want you to solve for energy, but instead of giving you frequency, they gave you just the wavelength, you have to use this formula. With this formula here, remember Planck's constant, which I said, make sure you write this down, is 6.626 times 10 power negative 34 joules dot second. Remember, c is the speed of light. You can use this as 3.0 times 10 power 8 meters per second. And then they will give you wavelengths. Now, the wavelength may be given to you in nanometers, some number nanometers. Remember, for all the units to work out according to dimension analysis, you have to convert it to meters, okay? I am that student who, when I'm learning something new, y'all are such nice students. That wasn't me. When I was learning something new, I was grumbling, oh, why do I have to learn something new again? You know, like, I'm like, I look back at the younger me and I'm like, okay, but you went to school to learn though, right? Hey, I can laugh at myself. I can laugh at myself. But I went to school to learn, yet when I'm learning something new, I'm complaining about it. That was me, y'all. That was me. Now I work with a trainer, and when he's showing us a new move, I have the same attitude. You think after all these years, I have graduated from that. I take it in stride. Okay, so we have Planck's constant. Once again, make sure you write this down. These are the kind of things that you want to know, you want to have next to you, because in this topic, you pull up Planck's constant, you use it all the time. Use the right value with the right. The issue with pulling stuff from online, there is constant, and in this is one type. So if you're just going online and Googling Planck's constant, they can give you the other one. And if you use that in a problem, you get your answer wrong and you're trying to figure out, I don't understand. I use the right Planck's constant. There are many Planck constants. The one you want to use must have joules and seconds, okay? Okay, we've seen this question. I have to delete it right before class as I was sitting here waiting, but I decided I'll leave it in because it does help us to get used to the term energy of photon. Energy of photon is the energy of the light. Okay, it would be like saying energy of atom when you mean energy of matter or energy of elements. This is just the particles in light. So saying here, arrange these three types of electromagnetic radiation, X-rays, microwaves, in order of increasing, we're saying wavelengths. So let's start with this. Remember, wavelength with how mellow, how intense wave is, right? The first picture here has a longer wavelength, so I'll say the wavelength is bigger, right? Because the space between the peak and the peak is big. Second one has a short wavelength. Excuse my really, really bad drawing, okay? So if you want to go from a small wavelength, I'll say here, small wavelength or short wavelength to a long wavelength, you're going from a high energy. I like to include that because my mind works with energy more than my mind works with wavelength. I don't know why. It just does. So I use that as an anchor to make sure I'm thinking things through correctly. Small wavelength goes with high energy. Long wavelength goes with low energy. And since I've gotten this far, remember energy and frequency go hand in hand. If I have high energy, I have high frequency. I haven't started to answer the question yet. I'm just placing my scales, right? High frequency, low frequency. Okay, So I have my two extreme ends. Then I remember the electromagnetic waves. Let's see. Visible light, that was what we saw. Visible light in the order of Roy, G, Biv. V had the highest energy. I remember red has the lowest energy. They didn't ask me for all that, but this is the process by which I remember. Okay. And then remember microwaves. Microwaves, even though my country said were really, really bad for you, they were technically lower in energy than the red light, right? So microwaves. The other way I used to remember things, since I had to take exams and stuff like that, and I knew my memory wasn't the greatest, I told stories, or if I didn't tell stories, I made up stories. My mind works better to remember things when they're part of a big picture, right? I realize my mind works a lot better to recall things. If it's just information by itself, it's hard for me to remember. So microwaves, because I have personal experience with that, the government said you can't use the microwave. That's lower in energy. And my argument was it's lower in energy compared to even light or ultraviolet light. So that's lower in energy. Then X-rays. Whenever I get an X-ray, I panic because it's high energy. It's right next to gamma rays. So once again, right, X-rays is higher than visible light. So yeah, there we have it. We have high energy on the right, low energy on the left. So after all that, the high energy here, I'll put X-ray, okay, for the first one. And then I'll put the middle will be visible light. And over here, I have microwaves. Okay, so the small wavelengths, this is going to be low wavelengths, X-ray. The biggest wavelengths will be microwaves. And then the frequency, when they say from low frequency to high frequency, I actually have to reverse the order because it said from low to high, right? So technically for that one, I have to reverse it. I'll say micro, visible light, X-ray. So with this one here, since it said increasing from low to high, I'll put my high energy here and then my high frequency. Remember, energy and frequency have the same trend, right? And then low energy here and then low frequency. I would say with chemistry, really find a way that works for you. It's not just chemistry, it's life, period. But we're starting here, right? We're not just going to school to get information, we're learning about ourselves. So find a way that works for you, how you relate to things, how you learn things, and then use that to your advantage. It will really, really help you in school and it will help you enjoy the process a lot better. Okay? And this is how I learn by applying it to my life. I call myself a selfish learner. Hey, it works for me. So once again, when it comes to frequency, remember frequency and energy have the same trend. So you can see here, same trend. This is the highest frequency. This is the highest energy. And of course, the other end is going to be low frequency, low energy, right? When it comes to wavelengths, the order is opposite. This would be the highest wavelengths and then the lowest wavelength. Okay. So after all the experiments, now we're moving on. We're trying to get to that quantum mechanical model. When do we get to it? Einstein concluded from his experiment, light is quantized. I already told you that, right? Light is quantized, meaning that when light is being shined on a particle or an atom, the way the atom receives the energy from light is not a continuous source. It's a packet, kind of like a packet of information or like a burst. So he found out that the ejection of the electrons from the metal surface by light occurs when the electron has absorbed enough photons of energy to escape. This should be from the atom. When irradiated with a shorter wavelength photon, the electron absorbs more energy that is necessary to escape. Remember, they're trying to connect what we just learned here, what we just reviewed. Small wavelengths goes with high energy. So chemists communicate like that. And it took me a while to realize that's how they communicate. They just communicate differently. I'm like, if you're trying to talk about energy and absorbing energy, why aren't you sticking with energy terminology? They're saying here, when irradiated or when shown, when energy is being shined on the atom, the energy has shorter wavelengths. Remember, short wavelengths means high energy. If the energy has short wavelength photon, the electron will absorb more energy. The electron only absorbs more energy if there's more energy available necessary to escape. The excess energy, because it has a lot of energy, becomes the kinetic energy of the ejected electron. Remember I told you the electron sprints off the surface? Right. So the greater the energy irradiated, which just means shined on, the greater, they call this the escape velocity. Escape velocity. And I was like, why do they sound like these electrons are bound against their will? Escape velocity, okay? So now we're moving on finally to the atomic spectrum. So we are warming our way eventually to the quantum mechanical model. We aren't there yet. So we're told when atoms or molecules absorb energy, the energy is often released as light. So bottom line, here's a picture of an atom. When the atom absorbs energy, the energy will not stay in the atom forever. The energy will eventually be released. So here we have energy absorbed, and then here we have energy released. For some reason in my summer class, this chapter lands right around July 4th weekend. So I can talk about fireworks, right? We see the application of this, again, somebody monetizing chemistry in fireworks. One of the things I would love to do if I had the opportunity is to go to a firework company and see how they put the chemicals together, right? To produce all of those patterns. I know the chemistry behind it, but I want to know the engineering. That part I don't know. The chemistry is the atom absorbs energy of light. And then when it's releasing the energy of the light, depending on the frequency or the wavelength of light, we get to see the different colors. So if you have the fireworks that are showing red, it's because the wavelengths being released goes with the red color of light. If you have yellow, different colors, once again, the different colors we see correspond with the different colors of light. Neon lights, when you're driving through a street or neighborhood at night, if they have a lot of those neon signs, hot pink, green, orange, whatever, all of that is using chemistry in a practical way. Those are all the lights you're seeing come from atoms losing energy. So light is essentially atoms releasing energy. So I should say releasing absorbed energy. Okay? So I'm sitting here talking to y'all and I have the light on in this room. So you know, as I'm talking about this, I am benefiting from this technology, right? So we're told here when the emitted light is passed through a prism. So now we're talking about the light that's being released. A pattern of a particular wavelength of light is seen that is unique to the atom of molecule, or atom or a molecule. So here's the thing. What they're saying here is once the atom absorbs light, actually, let me write all this down here. Here's a picture of it. The atom absorbs light, right? That's the first thing we're seeing. Absorbs energy. It doesn't necessarily have to be light. It can be in many forms, number one. Number two, atom releases energy. Energy is analyzed. Okay? So when the atom absorbs the energy, the atom eventually has to release energy because the energy it absorbs is not its own natural energy. The atom has to release the energy. But when it releases the energy released may not be in the same wavelength of the energy that was absorbed. It may release it in parts. And when it does that, the energy is being analyzed. Okay? So here we're told to analyze the energy, it's passed through a prism. So this will be one of the experiments that you guys work on. When the energy is passed through a prism, the light that's actually released has a very specific pattern. That pattern is called the emission spectrum. So here I give kudos to the chemist who named this. I like this name. Emission means release. You know how the government says, make sure your car is not emitting. Emitting is another term, it's a scientific term for release. So emission is the abstract noun of releasing, emission. So emission spectrum. This is the spectrum that is formed when you are analyzing, you're trying to split the light that got released, right? So this is released light. So it is a spectrum, but it's a spectrum from the light that got released, okay? So we're being told here, in general, there are two kinds of emission spectrum. There is a non-continuous one called a line spectrum, or there's a continuous one which comes from white light, okay? The continuous one, since tie-dye is in right now, I try to stay hip, y'all. I try, even though I don't own tie-dye, but tie-dye is in now, right? So when I look at tie-dye, one of the features of tie-dye is to get those colors to kind of blend into each other, right? You have different colors blending together and stuff like that. The continuous spectrum to me looks like tie-dye of light colors. So you have the light blending into each other. It's continuous, because to me, I'm like, continuous, I might see continuous, but it blends into each other. The light blends into each other. So here you don't see the gaps in the light colors, versus the non-continuous or line spectrum, you can see the gap. In the non-continuous, it's almost like the line spectrums are quantized, right? You have a specific light, then you have nothing, darkness, then light, then darkness. And I have, of course, pictures to show you that. So bottom line, before we go and look at the pictures, we're told here, the line spectra can be used to identify elements present in materials such as elements, since each element has its own unique line spectrum. Okay, so the line spectrum can be used as a tool. Once you figure out the line spectrum of the element, that line spectrum can be used as a tool to identify what the element is. Okay, I went to a workshop one time where they used the line spectrum to identify a poison. So it was one of those murder mysteries that incorporated chemistry. And the idea here was they used the line spectra to identify the element. Well, in the context, the element was the poison that was used to kill Madam, I forget her name. I told y'all, I forgot. But it was a nice story. I enjoyed the story. So somebody killed her, and they're like, what did they kill her with? We don't know. Let's take a sample of her blood and do analysis. And they figure out the line spectra, and the element was arsenic. So this is like one of those old school elements they used to, yeah. Anyway, yeah. It was an interesting story. I forgot the name of the people. But line spectra, once again, when chemists see something that's unique for the element, they always kind of get excited and say, we're going to use this to identify the element. So here's one of those things. Remember, line spectra is used to identify the element. I feel like at some level, the airport security uses this. They have yet to tell me the technology they use. I asked them one time, so what exactly, this machine that you're using to analyze the sample I have, my perfume, what exactly is the science behind it? And they look at me like, sis, you're going through security. Why don't you focus on that? I'm like, I am a teacher. I'm trying to incorporate this into my class. They never did tell me. I feel like what they're doing has something to do with this. They take a sample of whatever they've confiscated from you, and then they put it in the machine, and then they read something, and then they say, oh, you're good, go. I'm like, what are you seeing? I am special like that. Okay, now your experiment where you're trying to figure out Bohr's model, you're going to be analyzing the sample. So here, Bohr's model was successful around the hydrogen atom. So for us to analyze hydrogen atoms, since hydrogen is a gas, the gas is pumped into this spectral tube. This is called a spectral tube. Spectral referring to the spectrum here, right? This one here. This is a spectrum, like a graph. The spectral tube, you just pretty much pump hydrogen gas. I'm going to write here, pump in H2 gas. So the gases here kind of looks a little orange, and then electricity is passed through. So the spectral tube is attached to electrical source. So there's electrical source down here, electrical source. Since we don't get to see this in ourselves, the spectral tube looks like a bulb, but it looks more like a fluorescent bulb where you don't have that metal piece of metal in there, not like the incandescent light bulb where you have the piece of metal filaments, right? There is no metal in here because in the filament, the metal is your element. Here, our element is in gas state. Okay, electricity is being passed through. You can see here where the electricity causes the atoms to light up. So they light up into a color. The color is usually kind of like a purple color. So the light release is purple, and you can see that. But our question is, what is inside this purple color? So for you to analyze that, you have to use a prism. What does the prism do? The prism separates the light coming out of the source, our source here being hydrogen gas. It separates the lights into the different wavelengths. The component just means what is inside, the different wavelengths. So based on what we're getting here, what we're seeing is, let me see, I'm going to count 1, 2, 3, 4. I can conclude the purple light from hydrogen is composed or contains, right, of 4 different wavelengths. Right. So the purple light from hydrogen actually has 4 different wavelengths. So essentially the 4 different wavelengths or different colors mix up to make that purple light, what appears as purple to our eyes. So you can see here, in essentially to make purple, you have this one here looks like violet. I think they call it blue violet. This one is blue green. And then this one here, I don't know. And they all look kind of like blue to me. Let's just call that blue. And then this one here is red. Okay, so when you guys are working on your experiment, realize in the experiment they will tell you what the colors are. Let me detour real quick, by the way, so y'all can see what I'm talking about, because I know what I'm referring to, but I want to make sure y'all know what I'm referring to. Your next experiment, by the way, is a dry lab, so you shouldn't have to worry about not having your lab kit. This one right here, determination of quantum numbers. Where is it? There it is. So you see how they have a picture here, and it shows you, oh, this is the colors they have. Okay, well, we'll go with the colors they have: violet, blue green, red. So here they're showing you same setup, different picture, but you have the hydrogen gas here. Once again, it's passed through the slit. It's being analyzed by the prism being split. And then here you get 4 different bands. Okay, so they give you the nanometers, the wavelengths of each color. So you want to know this for your experiment. And I wrote here, the spectroscope and hydrogen emission tube are not part of your lab kit. So I've attached this image for you to know what you would have seen had we been in lab. Okay, so hopefully that shows you what you're supposed to be doing as far as your next lab is concerned. Where is my, right here. Okay. So we're told here each element has its own spectrum. Hydrogen has 4 distinct lines. So they're showing you the different spectrums, right? Remember how we talked about the continuous spectrum? This is continuous. Continuous. See, to me, it looks like a tie-dye of many different colors blending together. right? And all of the rest of these are line. These are line, this is line, this is line, this is line. It's obvious. The lines look like lines. The continuous looks like tie-dye fabric. Not really fabric, but you know the colors that bleed into each other like that. Remember, high energy, low energy. Okay. So helium can be identified by that. Barium, you have oxygen, you have neon. Of course, we've seen what hydrogen looks like. So now we're finally in Bohr's atomic model. Okay. So remember, I told you this is the most popular one, most popular as far as media is concerned. Bohr's model is used in the intro or the going from one scene to another in Big Bang Theory, Jimmy Neutron. Yes, I own that. I used to watch that when I was in college. Leave me alone. I'm not ashamed of it. Listen, I own my past. In the nuclear model, Bohr's atomic model, once again, just like Rutherford's model, these models come after these scientists have gained some insight from the experiment. So we're starting with the criticism, right, of Rutherford's model. Rutherford's model was great. We saw the nucleus, we saw the electron, we got to see all those different parts of the atom, but it did not explain the changes that occur when atom gains or loses energy. We've learned so much that the atom can gain energy and lose energy and release all this light. Rutherford's model explained none of that stuff. So then Bohr comes in and develops a model of the atom that will explain how the structure of the atom changes when the atom undergoes energy transitions. So we now have a new term called energy transition. So the term transition here will be talking about what's happening to the electron. Transition here is talking about electron movement. Okay, that's the context. I like the yellow color, it's more bright. Okay, so we're told here Bohr's major idea was the energy of the atom was quantized. Well, I already mentioned that because Planck mentioned that. I'm like, wait a minute, Bohr. If you're going to use somebody else's idea, maybe you should cite them. Anyway, Planck already said, and Einstein said, energy was quantized. Bohr is now saying the same thing. Energy is quantized, and that the amount of energy in the atom was related to the electron's position in the atom. So here things kind of get complicated, right? Bohr was studying the atom, but he keeps referring to the electron. So we'll see later on that Bohr's atom or his atomic model worked for an atom that just had one electron. So Bohr's model worked for hydrogen. And this is the bottom line I'm supposed to tell you guys later, but I feel like if you know it now, then you understand why he found what he found. He's saying the amount of energy in the atom is related to the electron's position. So if you have the one electron, that's all you have to work with. Wherever the electron is relates to the atom's energy. We talked about quantized. It means the atom could have very specific amounts of energy. I already talked about that before. So what is the summary of Bohr's model? He said electrons inside the atoms travel in orbits, and that these orbits are fixed distance from the nucleus. Okay? So we're looking at the atom. Remember, this is the planetary model of the atom. That's Bohr's model, called the planetary model. He essentially says you have a nucleus. There was no question the nucleus was in the middle. But around the nucleus, you had the orbits. And these orbits were a fixed distance. Oh, I'm not good at drawing circles. Around the nucleus. And on the orbit, you will find the electron. The electron can have many different positions, but there, even though I'm drawing many electrons, this is all the possible positions the electrons could have. Okay, it could be, let me call it E1, E2, E3. The electron can have many different positions. Okay, so we're not just studying one electron, we're studying all the possible positions of the electron or electrons. Okay, so he said that the natural state where you normally find the electron is called the stationary state or the ground state. So when I was learning this years ago, to me, stationary means you're not moving, right? So I like the term ground state better, but you want to be aware of both states. What they mean by stationary state is not moving from one energy level or one orbit to another. The stationary state or ground state, or what I like to call the home state, where you normally find the electron at home, the home orbit, we're told that this is the energy of the electron. Once again, the ground state has energy, and that was proportional to the distance of the orbit from the nucleus. If the electron was very far away from the nucleus, it had higher energy. If the electron was very close to the nucleus, it had low energy. So let me go ahead and write this down somewhere because I'm trying to paraphrase what's being said here. So according to Bohr, electrons close to nucleus had low energy. This is all relative, right? Electrons far from nucleus had high energy. I feel like with time my spelling is just getting bad and I'm writing a lot too. Okay? So for me to relate to this and not mix them up, I always envision this to be one of those stadiums, right? Like where they play sports and like an ice hockey stadium, something like that. But it's more round than it is like oblong shaped. And instead of you being on a seat, you are right in the middle of the stage or of the where the people play the game, wherever that's called. Yeah, you're right there and you're looking around. And where you're standing right where people play the sport or do the concert or whatever, that middle part, that is where the nucleus is. So the row where people sit will be the orbits, which we'll later call energy level, right? So you have a center right here, then you have these orbits around it. So if you have an electron that's very close to the center right here, E1 will have low energy. And then let me call this E3 will have relatively high energy. Okay, that's what he's saying. Electrons emit radiation when they jump from an orbit with higher energy down to an orbit with lower energy. The emitted radiation was a photon of light. The distance between the orbits determined the energy of the photon of light produced. Okay, what do they mean? Let me call this one here E2. Now, when they write that slide, they kind of skip what happened. Let's look at E1 and what's happening to E1. Let's say E1 electron is about to transition. Let me move this up so y'all can see. Transition. Okay, so E1 went from energy level 1, and even though they haven't defined this now, it's easier for me. The energy levels or the orbits are labeled N. So I'll say here moves from N equal 1. N equal 1 is the lowest energy level. So let me label this N equal 1. This next one will be N equal 2. This is N equal 3. Moves from N equal 1 to N equal 2. Okay, so for the electron to move from N is 1 to N is 2, it has to absorb energy. So after absorbing energy. Okay, let me backtrack a little bit, okay? Because I'm trying to go with the PowerPoint, but I'm going to kind of just freestyle for myself right now so I can explain this analogy. Hold on, this is my brother. Let me let him know that I am in class. Okay, there, he got it. Okay, so E1. Let me assign simple numbers so we can deal with this. Let's call this 100 joules. And then we'll call this 200 joules. Then we'll call this 300 joules. That's relatable, right? These are not the actual values. I just gave these numbers to that. So electron 1 starts off at 100 joules orbit. And it's trying to move from N1 to N2. It has to absorb energy. So one of the things that he mentioned, that Bohr mentioned, is the electrons close to the nucleus had low energy. Example, E1 only had 100 joules. The one that's far from the nucleus had high energy. For example, E3 had 300 joules. Okay? So the one thing that he hasn't mentioned here is the energy of the electron matches the energy of the orbit. Okay? So it's almost like if the electron has a lot of energy, it's allowed to be, the electron's energy has to always match the orbit energy. So if E1 absorbs energy, and it absorbs, let's say, 100 joules of energy. So right here, absorbs energy. Let me specify the amount. Absorbing 100 joules of energy. That allows E1 to move to N2. Why? E1 now has 200 joules of energy. So it gets to transition up to the position that's equal to 200 joules of energy from where it was. But remember I told you guys earlier, if the electron has energy that's not its natural own energy, then it's going to lose whatever it gains. So I think about it, it's kind of like, you got money quick and then you kind of lived a better lifestyle, living that life. And then you spent the money and you lost it. Then you're going back to living the old life you had. That's kind of how I see this. Anyway, the electron has to lose the energy. So now E1 will lose the 100 joules of energy it gained and return to N is equal to 1. Okay, so first it gains the energy and transitions to a higher energy level. But when it gets there, it's there for a while, then eventually goes back home to its ground state. As it's going back home, it has to release the energy it gained, and that's what we see as light. So there's a whole story behind this, right? So back to the slide, they were saying here, electrons emit radiation when they jump from a higher energy level to a lower energy level. That's very important. Only when they're going from higher to lower. When they're going from low to high, they have to absorb. Okay, because remember, wherever you find the electron, its energy must match the orbit energy. It can't be in the wrong energy orbit. And that's what experiments showed. Okay? Do y'all have any questions? I know I've been rambling on and on. Sometimes I get too much into this and then, it's like, yeah. Can the electron jump more than one energy level? Yeah, because Einstein showed different amount of energies that are exposed to the electron or the atom can cause atom to different amount of energy. If you have more energy is absorbed. So the electron, E1, let's give E1 a bigger adventure, goes from N1 to N3, all the way up here. So if E1 now moves from N1 to N3, well, being a little bit adventurous here, it has to absorb 200 joules of energy to have a total of 300 joules of energy, right? It can't just be in an orbit and not really have an energy that matches the orbit. And once it does that, when now it has this new energy, 300 joules right here, remember it went from the regular state. Oh, by the way, these two different states have a name. When it's on the original level, this is called ground state. We talked about that, the home state. And one is E1's ground state. That's where it's normally found. What I like to call is home state. When it's at N3 level, this is called the excited state. Yeah, if you got lots of money, I don't know. Oh no, what did I do? Sorry. I pressed the home button on my iPad. Okay, when you get lots of extra money out of nowhere, you get excited too. The electron is excited, but the excitement is not permanent, it's only temporary. At the excited state of E1 electron, where it's not normally found, it has to return back to its ground state. So when it goes back to its ground state, E1 will lose 200 joules, the extra amount again, to return to ground state. So I illustrated what they said here. The gap in the energy level relates to the amount of energy, right? More energy because the gap was bigger. So I want to move over here and show you this right here. They have the same thing. I don't know what's up with this picture. It's also in the book, but they're missing one of the bands. I'm like, y'all, did somebody forget a band? This is talking about Bohr's model and then the hydrogen emission spectra, but that's what they have in the book, so I just talk about it, right? They're missing the regular violet. So in your experiment, you're going to be drawing at some point when they say draw the planetary model. This is your planetary model. Don't say I didn't help you. Right here, this is what you're going to be drawing, right? You can draw the full model, you can draw the half circle. This works. They are missing the one purple, the violet over here. But this is showing you the possible electron transitions inside the hydrogen atom. So there are 4 possible ones. You can see the energy levels here. Remember, the energy levels are labeled by the symbol, the letter N. This is the nucleus. I'll call it Nu. N is 1 is energy level 1. These are the, what's it called? The VIP seats close to the nucleus. Energy level 2 is right here. Energy level 3. 4, 5, and somehow in this picture they're missing 6. I don't know what happened to 6, but it should keep going on. We need 6 to make this, right? So you can see, remember, as far as energy is concerned, red has the lowest energy. How does that relate to this picture here? Do you see what it takes to make the color red? The electron just has to go. So the electron's home state, let me erase all this so we can see. The electrons, all these electrons, right? Their ground state is energy level 2. How do I tell that's where they're going to? They're all going back to energy level 2. This is the ground state of the electrons. Okay, so this is showing when they're coming back, gone out there to have a good time. This one here is the excited state. When the electron got to the excited state, on its way back home, just undergoing this small gap, it was able to release and produce red color. On the other end, after jumping this huge gap all the way down home, huge gap, this one here produced blue violet. So that's how we know this has a higher energy, right? You see how it all comes together? Because the huger the gap, if you were that kid that jumped from places, you understand when you're jumping far, it does, or if you're climbing far, it takes a lot of energy. It took a lot of energy to get up here. It takes a lot of energy to go back down, right? Or you have to release a lot of energy. So remember, the gap relates to the amount of energy released and therefore the light we see. The bigger the gap, the more purple the light. The smaller the gap, the more red the light. Okay? Any questions about this in your lab? If you have any question, even though I know I'm going on and on and on, feel free to type something. I keep looking up eventually just to see if you guys have a question. But yeah, what I'm looking at right now relates to your lab for this weekend. So here, we're stepping back. We're kind of zooming out, right? And we're seeing or we're realizing hydrogen has more than just visible emissions. We're told here that technically hydrogen has all of these energy transitions. So hydrogen, I'll say here, has all of these energy transitions and radiation. The issue is when you go to labs are designed from the human perspective, right? With us as the focus, not what's, yeah, with us as the focus. If you look right here, what we're seeing is within the atom of hydrogen, all of these transitions are possible, okay? We're going from energy level 1. So this one here is showing you the electron absorbing energy. And somehow this particular electron here, they're saying ionization. Let me tell you what happens with ionization. Ionization occurs when electron absorbs enough energy to escape the atom. Okay, this electron is not going from one energy level to another with the goal of coming back. Do you see that one-way arrow? That's like buying a one-way ticket. This electron is gone. It's gone out of the atom completely, so it can't even go back to a lower energy level. You can see right here. Ionization, it goes from energy level 1 to infinity. In other words, it's gone. It bought a one-way ticket out of the atom, right? On the other hand, here they're showing you there's so many other transitions that occur. So all they're showing you is the second half of the story. Once they're at the higher energy level as they're going back home, right? So you see right here, these series here, these produce, I don't want to say light, they produce radiation that's in the ultraviolet wavelengths. Well, we can't see this. We can't see ultraviolet radiation. We really can't. If you buy one of those black lights or blue lights or whatever, we technically can't see it. What the engineers or the designers of the equipment do, they add a different color light so it can warn us so we're not looking right into the light that we can't see, right? We can't see light in the ultraviolet region. Just like we can't see the actual wavelengths. And then we can't see light in the infrared region. It doesn't show up to us as color. What we can see is the visible region. So in the lab, even though you only record these four for hydrogen spectrum, technically this series is being produced and so is this. Only the human can't see those. We can't see. This one here, we can see. So your experimental results will only show 4 bands, right, from hydrogen. But in reality, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's technically 10 bands, but we can only see 4. So we only report what we can see. But we know theoretically there is more. Okay. Now, if you have special goggles that allow you to see ultraviolet wavelengths, then you'll be able to see this being released. As the electrons go from a high energy level, it shows you here from 5 to 1 and on and on. I'll skip over here and continue. Okay, so after we've seen that, how does the quantum mechanical model, we haven't really reached that. We're still talking about the Bohr's model. How does the Bohr's model, I think this one here should say Bohr's model, not quantum mechanical model. How does it explain what's happening with the atomic spectrum? We learned that each wavelength in the spectrum of the atom corresponds to an electron transition. Each of the light we see, right, back here, if we saw the purple, the violet, sorry, blue, violet, blue, green, or red, either one of those wavelengths correspond to an electronic transition between orbitals. We're told that the excited electron, when the electron becomes excited, it's because it absorbs energy applied and transitions from a lower energy level to a high energy level. This happens for it to be excited. And then once it's excited, when an electron relaxes, it transitions from an orbit of higher energy to an orbit of lower energy. So this is a summary. Yeah, this should say Bohr's model. I don't know why it says quantum. Bohr's model. We're trying to figure out what we learned from here that then transitions us to the next and better and the final model. Okay. When the electron relaxes, a photon of light is released whose energy is equal to the energy difference between the orbitals. Okay, so we already saw that. We discussed excitation, and so I'm not going to talk about that again. Once again, remember this one here is this absorbs. This one here emits. Remember, the same thing as release. Make sure you have these words written down, because if you don't know the words in chemistry, people say chemistry is math, and I'm like, no, it's not. Yes, it is. I'm like, I'm not going to argue with you. Okay. Chemistry uses math, but chemistry is not math. Math is just a tool that chemistry uses to confirm the concepts. So if you ignore the words they're using here, then you have no idea what they're saying. Words like emit means release. Could they have used the word release? Yes. Did they? No. Have I thought about writing a letter? I don't have time for that. But here, you have to be familiar with the words they use so you understand what is being communicated, right? Math is used heavily in chemistry, but the math just supports the words that are being communicated. Finally, we're now trying to figure out exactly. So there we are with the math, trying to confirm what we learned, right? We learned this stuff about the energy, but now we're about to confirm it. We're going to be looking at the energy transitions in hydrogen. So we know hydrogen produces these four transitions of light, or yeah, these four transitions that correspond to color light. We're trying to figure out what is the energy of the light release. We know the blue or the violet has high energy, the red has low energy. But if you're asked to produce or to write the value of the energy, how do you write that? For that, you need this equation right here. Okay. And we're told here, so the change in energy of the electron is the final state minus the initial state. So you have the energy of the electron versus the energy of light released, right? So this here is the energy of the electron. I'll just tell you here, when they're asking you to figure out the energy of the photon or the light released, instead of going final minus initial, just look at the energy level. If we're starting from energy level 5 to energy level 1, if the electron is going from 5 to 1, then that's what you figure out. The energy of the initial state where it's starting minus the final. So from here, the energy of the initial state minus energy of the final state. So the energy of the electron is opposite in the sign from the energy of the light. At this level here, the most important thing you be aware of is the energy of the light. So even though we have this equation right here, I would say this. This equation goes with energy of the electron, but make sure you write it down nonetheless. And I'll show you how it kind of works out to solve what we need. Okay. So write this down. We're going to be doing some math before I release you guys. I'm writing it down too, so I don't have to go back and forth. Oh, I need to define Rydberg's constant. Okay, this number here, 2.18 times 10 power negative 18 joules, this is called Rydberg's constant. Rydberg's constant. A scientist that came up with this constant to help us figure out the energy of the electron when it goes from one level to another, okay? I bring it up because it's in your lab where they tell you, what is Rydberg's constant? Write it here. So you want to have Rydberg's constant. Okay. So we're going to be working this out. It says, determine the wavelength of light. So we're figuring out the wavelength of light versus the wavelength of the atom, right? Find the wavelength of light emitted when an electron of hydrogen atom makes a transition from orbital energy level 6 to energy level 5. So the electron is going from energy level 6 to 5. So it'll be like this, right? N is 6, N is 5. It's doing this. And they're asking you, what is the wavelength of the light release? Okay. Now, when we do the math, we tend to get the energy in meters, sorry, the wavelength in meters. So you're going to get it in meters first, and then you convert it to nanometers because that's the normal way of doing it. Okay. So let's go ahead and move on. They're telling you here. Now, they start off by figuring out the energy of the atom. Then they go from atom to photon. I'm just going to go straight to photon. So what I'm going to do here is the energy of the photon will be from energy 6 minus energy 5. Okay. So from energy 6 to energy 5, essentially what happens here is this modifies our equation to where we have, let's see, they had energy final, which is 5. So our equation will be negative 2.1 0.18 times 10 power negative 18 joules. And I'll write 1 over energy initial, 1 over energy final. Okay? Or we can just change the symbol here. So what I'm going to do, I'm going to work this out. I'm going to use a different symbol here. This would be positive. So let's go ahead and set this up. And I'll show you how this works out. So what we're doing here is we're trying to figure out the change in energy of the photon. So what I'm saying is, instead of doing E5 minus E6, I'm doing the energy of the photon, okay? The energy of the photon is opposite in charge, just the charge part, to the energy of the atom. So I'm going to do here, instead of doing what they're doing here, I'm going to reverse this and say energy 6 minus energy 5. So for this equation here, the energy of the photon will be the same number we had, the same equation we had, only it would be a positive version. So it would be 2.18 times 10 power negative 18 joules. And then I'll leave everything as is, 1 over n final squared minus 1 over n initial squared. Okay? So we were told in the question that the electron was going from energy level 6 to 5. So we know that n initial, it started off from 6. It ended up at n level 5. So we want to eventually find the wavelengths, but for us to find the wavelengths, we have to find the energy. Based on the information given, this is the only equation we can use right now. Okay? So the energy of the photon is equal to 2.18 times 10 power negative 18 joules. And I'll show you once we get the joules how this works out. 1 over the final position is going to be 5 squared minus 1 over initial 6 squared. So mathematically what I'm going to do here is, I'll use the red color. I will work this part out first and then bring this in. So I'm going to do 1 over 5 squared minus 1 over 6 squared, and then plug this in when I'm done. I'm putting this in my calculator, which I haven't used in a while. Open parentheses, 1 fraction 5 squared to the right minus 1 fraction 6 squared to the right, close parentheses. Oh, come on, calculator. Okay, this puts me at 11 over 900. No need to panic. So now delta E photon is 2.18 times 10 power negative 18 joules times 11 over 900. So if I multiply this out, it should work itself out, and I should get my energy of the photon in joules. Okay, so I would say that you guys, when it comes to solving problems, since most of your questions will be about the photon, I would say this is the formula you should use. Okay, the energy, if it's going from a higher energy to a lower energy, will always be positive, not negative, because it's releasing energy. Okay, so let me multiply this number. I have 11 over 900 times, open parentheses, 2.18 exponent negative 18 to the right, close parentheses, and I get 2.66 times 10 power negative 20. That's my energy of photon. Okay, remember the energy of photon is always positive. So say you mess around and you forget and you use the original formula that has a negative, just change the number to positive. Okay, but they didn't ask for energy, they asked for wavelengths. So this is where you go, oh, wavelengths. Okay, so for the wavelengths, let's see, remember we had energy, change in energy was equal to Planck's constant times frequency. In the place of frequency, we put speed of light over wavelengths. This is what we're trying to solve for. So to solve for wavelength, let me quickly rearrange this. I'm going to just switch positions of this and this. Wavelengths equal Planck's constant times constant speed of light over change in energy. I have Planck's constant as 6.626 times 10 power negative 34 joules second, right? Speed of light 3.0 times 10 power 8 meters per second. So I have this, I have this. I just got delta E as 2.66 times 10 power negative 20 joules. Okay, where was I? Oh yeah, so plug everything in to get wavelengths. You see how the units map? Joules, joules, second, second, meters. So my wavelength will be in meters. I know that. So 6.626 times 10 power negative 34. Use parentheses. I cannot say this enough. In your calculator, until you're super comfortable and you know how your calculator works, the safest thing, use parentheses. 3.0 times 10 power 8. It makes your work more efficient. You get more answers right. And then you just overall, I cannot guarantee happiness in life, but we can talk about chemistry, right? So use parentheses. They are your friend in your calculator, okay? Joules, joules cancel out. Second, second cancel out. Our answer will be in meters. Okay, so using parentheses, open parentheses, 6.626 exponent negative 34 to the right, close parentheses, times, open parentheses, 3 exponent 8 to the right, close parentheses, divided by bottom number, open parentheses, 2.66 exponent negative 20. Close parentheses. Oh, no, 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 no. I'm supposed to go to the right. Hold on a second. To the right, close parentheses. The parentheses was in the air. Can't have that. Okay, so I did all this math and I have 0 0.1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 7, 4, 7. My number looks slightly different. Oh, I guess. Meters. This is what I get from my wavelengths. Let me move the meters close by, so far away. But remember I told you guys they write wavelengths in nanometers? So you want to convert. 0.0 wavelengths equal to 0.00050. 1, 2, 3, 4, 5. 0.00747 meters. Use the conversion right here. 1 nanometer. Nano stands for 1 times 10 power negative 9 meters, right? Meter, meter cancels out. And then what I get here when I multiply this is times 1, the number I have, divided by, open parentheses, 1 exponent negative 9 to the right, close parentheses, equal. So my answer ends up being 7472, 3 round up nanometers. That's my wavelength. When you look at it here, well, their answer is slightly different because they rounded out differently, but our answer is very similar to that. Okay, so let me see what we have here. I know we are at that 1 o'clock mark, but I'm also realizing that we're a little bit behind on this part here. So what I'm going to do here, let's see. When we come back, I want to start on the quantum mechanical model right here. So I'll just go over this when we come back. We do start a little bit later every day, so it's like we're running out of time. But I'll just start here. When what we can get done, we can get done. Okay. Oh, I guess I should write start here. So yeah, this is where I'm going to end for today. Let me see. Someone emailed me to ask me about a question with the, was it volume? I forget what the question was. Let me see. I don't think she's in this conversation, but do you all have any questions about, do you have any questions about the lesson? Any questions about homework or lab? Or anything that I've discussed in the past? I want to give you guys a chance for that. Okay, Once again, if you have any questions, I guess since she's not here right now, what I'll do, I think she was asking questions about calculating the volume of the sphere, and I forget exactly what the question was. Where is my phone? Let me see. I think it was something I covered in the end of chapter. I want to say chapter 1, E1 or whatever, or maybe either E or chapter 1, and she asked a question about that. So what I'm going to do is see. Oh, okay. So yeah, so what I'll do, I'll meet with her and then I'll record that session. So once again, if you guys want one-on-one sessions with me, email me, let me know, because I do have office hours from 2 to 4, but most of you, you have a different schedule. We are required to have set office hours. I don't necessarily, I try to be available. When I say available, I mean like in the city. But if you have a work schedule that does not go with my office hours, email me and let me know. If I'm available at that time, I will try to make time to talk to you about something specific, right? If you, for some reason, your work schedule doesn't work with my office hours from 2 to 4. But when it comes to, and the question that she asked here that I can discuss right now, do we need to memorize the charges and masses of subatomic particles? Yes, it will help if you memorize the charge and the mass of the subatomic particles. So, especially if you're a pre something like pre-dental, pre-med, pre-vet, whatever, the more you memorize, the better. And if you're bad at memorizing, find a way. For me, since I know I am bad at memorizing things, when I write things down, the more involved I am in the subject area, whatever I'm trying to learn, the better. People don't like the way I learn, aka my husband, but that's for neither here or there, because I ask a lot of questions. And he's like, well, if you let me finish, I'm like, this is how I learn, though. I have to be involved. So he would start talking and I already have a question. And I'm like, but at least I'm listening. So if you're the kind of person who, for you, memorizing is a little tougher, find a way that works for you. You want to explore different ways of learning and then find a way that works for you and then stick with that. Okay. Since I know I'm not very good at memorizing, I have to be involved. When I show up to learn something, I have to show up to ready to be super involved. The less involved I am, the less I am learning. I write stuff down, even though some things I have zero intention of reading, but the act of me writing it down forces my brain to process what I'm reading, right? Or what I'm writing as I'm listening. I have to repeat it. So when I get done learning something new, guess who's getting called? One of my poor friends. Hey, Sophie, let me tell you what I learned today. I really don't want to know, but you're going to listen and hear. And then I repeat it. And before you know it, I've learned it. So I talk about it. I write it down. I try to repeat it. I try to apply it to situations that have nothing to do with it. Yeah. And my friends look at me like, you learned something new, right? I'm like, yeah. But this is how I learn to be involved, right? And then I learn, and then when I learn it just gives me more knowledge base. Okay. Terminology is very important. And so all I'll say is when you're reading, you want to ask yourself, what are they trying to communicate? This is a new word I haven't seen before. What does a new word mean in this new context? And so it does help. It helps a lot. Then if you want to take any more chemistry, I'm not advertising for chemistry, trying to give it a shout out. If you want to take more chemistry, they use those same words in different level classes. By that time, you're more aware of these words. Come organic, if you're doing organic, these words are not new to you. The word emit, translates, all those words are not new to you. Okay. So if you guys don't have any more questions, we'll wrap this up for today. Let me see. I need to make a plan for you guys' exam because I have different classes that have different exams at different times. Your exam is on the 21st. Let me see. I should know what day of the week that is, right? No, I don't have those things memorized. I'm proud of myself for knowing what day of the week every day is. Okay. Oh, that's good. So we do have some time. I shouldn't panic. We do at least have 2 days to go over quantum. So we'll go over the remaining chapter. and go over quantum. So hopefully we can see it twice, and then that will make things okay. Please work on the lab. That way, if you have any questions, you can bring it up next week. Okay? Other than that, I won't see you till next week, so have a nice weekend.